Okay, so this is lesson and 3.1, but this is notes 12b. You might be saying, well, why is she doing lesson 3.1 in chapter 12? We're going to go through these topics in chapter 3 first, and then we're going to integrate the matrices into it. So some of the stuff you already know. You know about graphing, solving systems graphically, solving systems algebraically. We're going to talk about that. Then we'll do it with 3 variables. That'll be new for you. And then we'll start bringing matrices into it. And that's kind of interesting and a really kind of cool way to solve complicated problems. So that is the plan. Now, let's get started on 3.1. See if I can make that a little bigger. Okay. So the objective is you can solve a system with 2 variables, and then the other objective here is that you'll be able to identify a system as consistent, inconsistent, as well as independent or dependent. So the definition of a linear system consists of linear equations, so they're lines, okay, and a solution of the system is a set of values for the variables that make all the equations true. So you can solve a system of equations graphically or by using tables. You also can do it algebraically, which is what we'll be talking about. We actually aren't going to do a lot with tables because that doesn't work all the time. So it's, I think, kind of not worth talking about. Okay, so if you have, I'm going to take this equation here, and you have negative 3x plus 2y equals 8. And what you want to do is, when I try to solve this graphically, is I typically try to get them in y equals mx plus b form. There are other ways to do it. There's a way where you find the x-intercept and the y-intercept, but I feel like this is kind of the tried and true way to do it, is just always get things into y equals mx plus b form, because if you get into y equals mx plus b form, then you'll know the y-intercept, that's b, and you'll also know the slope, and so you can just go ahead and graph it, because then, you hopefully we're pretty good about graphing lines. So I'm going to add 3x to both sides to get this in y equals mx plus b form, and you should be writing this down in your notes as well. And then we're going to divide by 2, and you can either like divide the whole thing by 2 like that if you want to, or you can, usually it's just like divide everything by 2, so I usually write it like this. And then those 2 cancels out, so you have y equals 3 over 2x, and then 8 divided by 2 is 4. So your y-intercept is 4, and then you're going up 3, 1, 2, 3, and over 2. It's a positive slope, so as you read, it should be going up and to the right. And down 3. Now I'm going down and over 2 because I'm trying to think I'm doing this. This graph is actually pretty small for me to read, so I hope I'm doing that right. Okay, so that's one. I might just keep those points. You can draw a line in there if you think you can. I just think I'm going to mess it up if I do that because that graph is so small for me. And then the other one is x plus 2y equals negative 8. So subtract x, 2y equals negative x minus 8. Divide by 2. Remember, in front of this x, there's like a 1 there. So if you're going to write it in slope-intercept form, it's going to be negative 1/2 x. I try to write the fraction out in front so you really can see that slope, and then minus 4. So minus 4, 1, 2, 3, 4, right there. And then it's going down 1 and over 2. This is a negative slope, so it's going down as you read from left to right. Oop, that's where they intersect, you guys. It's so exciting. When you do this graphically, typically when it asks you for a graphing problem, the answers are going to be nice integers, because if they were gross numbers, like decimals or whatever, you would graph it, you wouldn't quite be able to tell where they intersect. So usually for graphing problems, they're nice answers. So then this intersection, and again, you could draw lines through there. Technically, you should. I just think, like I said, I'm going to mess it up. 1, 2, 3, 4, negative 4, comma, negative 2. So they are intersecting at negative 4, comma, negative 2. So your solution is x equals negative 4, y equals -2. But again, often you write it as an ordered pair like that, with the x value first and then the y value like that. Okay, so that is a solution, and there was one solution. Those two graphs, there is only one answer for x and y that work so that those two equations both work, and that is -4 for x and -2 for y. And when you do it graphically, like we just did, it's an intersection point. Okay, going through some of these definitions now. So try to get a nice yellow here. So a consistent system, okay, has at least one solution. So like this one we just did, that was consistent. And then branching off from consistent, it's either independent, meaning it has one solution, just like the one above. That is a consistent system because it has a solution and it actually only has one solution, so it's independent. Or it's possible it can be consistent, but it actually has an infinite number of solutions. And that happens when you have a line and then you have like another line right on top of it. Okay, so if you give you actually two equations of the same equation, that's when it is dependent. And then the other little definition is an inconsistent system. So if there is no solution, it's inconsistent. And that happens when they are parallel lines. So if you get two equations like, let's say 2x minus 4 and another one equals 2x minus 10 or something like that, because the slopes are the same, but the y-intercept is different, those are going to be parallel lines. And you could say, hey, that system is inconsistent. So these are basically the three possibilities that you could have. And that is what we're going to do for the rest of the lesson. And it's going to be great. So looking at this one, it says, without graphing, is the system independent, dependent, or consistent? Now, again, if you can find a way to prove which ones of these are, they're exactly the same, you can do that. There's ways to play around with them to see if they're the same. I typically just change them to slope-intercept form. And if basically I have the same slope, then I know they're parallel or they're actually the same line. And then I check the y-intercept. And if that's not the same, well, then they're parallel. And if it is the same and the lines are parallel, then I know that it's basically a consistent system that's dependent because it's actually all the same line. And then if I get two different lines or two different slopes, well, then it's going to have one answer. Let's do this. All right, so I'm going to do the first one. 4y minus 2x equals 6. I'm going to get the x over to the other side. 4y equals 2x plus 6. I'm going to divide by 4. Y equals 1/2 x, because 2 divided by 4 is 1/2, plus, and this will reduce to 3/2. That would be kind of gross to graph. It doesn't matter. I don't have to graph it. All I have to do is see if it's the same. And now the second one was 8y equals 4x minus 12. Divide by 8 to get y by itself. Y equals 4/8 is 1/2. Ooh, they have the same slope. And then 12 divided by 8, if you reduce that, they have a factor of 4. So divide by 4, that's going to be a 3, it's 2, and it's negative. Okay, so these graphs or equations have the same slope. So they are either parallel or they are coinciding lines like you see here. They're either this one here or they're this. But their y-intercept is different, right? Those are not the same y-intercepts. So then these are parallel lines. So you could say the things it might ask you, like on your math Excel, is that this is an inconsistent system. You might say, if it says what's the solution, it would be no solution because parallel lines never intersect. And I think that's, you could say something like parallel lines if it asks about that. This question is just saying, what of these things is it? And so it is inconsistent, and that is that. Moving on, these 4, I mean, these we're gonna get some kind of examples for these 4 here. So let's all kind of the different possibilities, right? So without a calculator, is each system independent, dependent, or inconsistent? Now, if you feel like you could pause my video and see yourself, I mean, this would be a good opportunity for you to just kind of do it on your own by pausing and then check back with me. But I will, I'm going to pause myself and write some of the kind of work on some of the answers so the video isn't terribly long, but I'll show all my work. You pause it too, try to do them on your own, and we'll see how we do. All right, so let's kind of talk through these, and you can kind of take a look at your answers if you want to pause and not listen to me talk. But the first one, the equation, this first equation here, I get y equals 3x plus 4. The second one, a little harder to get y by itself for that one. I subtracted the x right there, and then I have this. I don't like this negative 1/3 right here. So to get rid of a fraction like that, I'm going to multiply by its reciprocal. The reciprocal of negative 1/3 is negative 3. So if I multiply both sides by negative 3, keeping it balanced, then negative 3 times negative 1/3, that just becomes 1. So then I just have one y, and that's like y. On the other side, I need to multiply by the negative 3, and I multiply it to both things, and so I get this. So you're looking at this equation here and this one here. They have the same slope, but they don't have the same y-intercept. So this is a situation of like parallel lines like this right here. Different y-intercepts, same slope. They are inconsistent. There's no solution. They're parallel lines. Let's do another one here. See if we get a nice light color for this one. Okay, so this equation here, when I get it solved for, I have y equals negative 2/3 x plus 1/3. The second equation, when I work on that one, I get y equals negative 4x minus 3. These equations don't have the same slope. They don't have the same y-intercept. So they're going to cross like at one point. So that is an example of intersecting lines like this. So they are going to be consistent because there is a solution. And because there's only one solution, we call that independent. C, the first equation looks good, right? That I don't have to mess around with at all. But the second one I have to play around with. So I'm subtract the 6x, divide by negative 3, and I get this equation. This equation is the same equation as the first one, right? So then that's an example. They're the same line. That's an example of coinciding lines. This is a consistent system because there is a solution. In fact, there's infinite number of solutions because all the x and y values would work if on any of these equations. They're the same equation. So then we call that dependent. So that's the lesson there. Now you should be able to go and do the exit ticket. If you want to go back and do the warm-up, it's the same Schoology assessment thing, right? So you could go back and do that. Remember that those you can do 3 times. That's how I have them set up. So you can do them more than once. If you make a mistake, go fix it. And so you get 100% in the formative category.